Hello, everybody. I hope everybody had a good weekend and did a bunch of studying quantum mechanics because that's what we're all about here forever. Um, I have graded your lab number threes and I uploaded those to Canvas, so hopefully you have received those. If not, check your assignments page and then click on assignment 3, and then you can download a copy of the worksheet that I have edited and graded. Just like last time, anything that I've made a comment in, I put pink around it, just because that was what color I picked the first day for whatever reason, and then I've just stuck with it. um, to give your pages a nice cyberpunk sort of blue and pink vibe, I guess. I don't know. Or baby boy and girl, whatever. We're going to continue with Chapter 3. Tomorrow we'll do lab assignment number 4 for the Q&A. That is online. I haven't actually hit the button, so you can't see it yet, but I will do that after class, and it will be available. Yeah, I am too. I'm very excited about that game. I'm a big Shadowrun fan, and I am definitely looking forward to playing it, even though it's not even the kind of game I normally play. But yeah, so there are no other announcements that I really have, so without further ado, we're going to talk about not this, because I think we actually weren't this far, were we? I didn't do electron configs of ions. Yeah, we were right. Were we here? Oh, I got to take this down for a second because it's the wrong slide. Sorry, I try and guess where we were. This is where we were, I think. Yeah, we haven't done ions yet, so we're going to do that today because that's important. All right, so we did electron configuration of any element on the periodic table before. Now we're going to do this for an ion. And it turns out for one of the directions, it's very easy. And that's the anion. So if you have an anion, you're just going to write the electron configuration as if it was an atom with more electrons. But if you have a cation where you take away electrons, then it's a little bit different. All right. And the reason for this has to do with where electrons are in proximity to the nucleus and how we get rid of electrons. And so what ends up happening when you remove electrons is they get removed in this order, which looks really stupid. Down here. But what these guys are right here, and it's barely going to fit on the screen here. When we remove electrons, we're going to remove the valence electrons first, because they're the electrons that are on the outside. If I was going to reach into a bag of potato chips, I'm not going to reach for the one at the very bottom in the corner, because then I'm going to get my hands all over them. No, you take the ones on the very top, right? Because you're not a gross individual that spreads disease, we'll say. Or maybe you are. Maybe you've been eating potato chips wrong. I don't know. But when we remove electrons, you always take the valence electrons first. And this is going to go back to those summary or summarized rules that I made for valence electrons, where we only do S and P electrons as valence electrons. And we're just going to ignore D and F electrons until they become the valence electrons. And then we'll remove them. Now remember that the valence electrons are in the highest N. And so when we look at an electron configuration, we're going to remove the highest N first. And we're always going to do that. So if there are choices between what N to remove, we're going to remove from the highest N first. So let's do a few examples and see that. So what's the electron configuration for O2-? So what I want to do is first figure out how many electrons O2- has. So if you have a periodic table handy, find how many electrons oxygen has, and then 2 minus it. What does that do? And tell me how many total electrons I should put in my electron configuration. You type it in the chat. And 10 is right. Very good. So if I have something that has 10 electrons, that's kind of like saying I have neon, right? Because that's 10 electrons. And so my electron configuration should be the same. And I'm writing this extra language here because now I can highlight the word anion. Because this method only works for anions. So what's the electron configuration for O2 minus? If it has 10 electrons, well, we'd write it exactly the same way. O2 minus. And then we would write 1s2, 2s2, 2p, 6. And you could do helium here, but it doesn't really save you any space. So I never do the shortcut for helium. Alright, so that's how we do an anion. And you could do any other anion that you want on the periodic table, because whenever you add electrons, it's like you're just going to the next element over and writing its electron configuration. And all of the old rules apply. So if I did, for some reason, like vanadium minus, that looks like chromium, so I would follow the D4, D9 becomes D5 or D10 rule. So, exactly the same. Oops. All my text is going to appear over what I wrote. So there you go. Now let's do a cation, because that's a little bit different. The best way to do this, and actually, you know what, let's go to the sample problem viewer here. Just because we have this canvas to write on, I might as well. Is that visible? Oh, sorry, I had another window over top the problem statement, so I was like, can you guys see it? Yeah, you can totally see it, I just couldn't. Alright, so whenever you're writing the electron configuration for an positive ion, so a cation, the way to do this is that you want to write the electron configuration of the neutral atom first. So if I was looking at iron, and you could do this with the shortcut or the long way, it doesn't matter. So 4s2, 1, 2, 3, 4, 5, 6. So this would be my electron configuration for iron in the neutral state. But now I want to make it +2. Which means I need to remove 2 electrons. And you need to remove the electrons from the valence shell. Oops. So remove valence electrons first. Alright. In my electron configuration here, what are the valence electrons? Which ones? Because I've got all sorts of electrons here. Which ones are valence? It's the 4s, and the reason for that is because those 4s electrons are in the highest n. And so I have a bunch of electrons here. This one is in n equals 4. This one's in n equals 3. These are the highest n, so we're going to get rid of them first. And that's convenient that there's 2 there because we need to make a +2 charge. So when I write my electron configuration up here now, the electron configuration for iron 2+ would just be Ar 3d6. There you go, that's the answer. I forgot where to click. There we go. So that's how we determine cations, is we get rid of the highest n first. And the reason for that is simply just because valence electrons are the furthest away from the nucleus. They're the ones that get grabbed first. So what I want you to do is I want you to write the electron configuration for each of these ions with no regard to whether they seem stable or not. So just whatever the outcome is or the result, write the electron configuration for them. And of course you can use a shortcut. Just be mindful of any exceptions and weird things. So like, for example, copper, Cu, When you write it out initially, you're going to have to write it out with the correct configuration, or else you'll get the wrong answer. So just be mindful of that. I'll give you 5 minutes to do that. We'll go over the answers in just a bit. Good luck. All right, how are we doing? Do we need more time, or are we ready for the answers? I saw one answer up there, and then suddenly it got very quiet. Oh, that might be why, because answers are coming in that are being paused. Yeah, go ahead and take another 2 minutes to go over the answers, or to solve these, and then we'll go over the answers. I don't know if you can hear, but there's a cat right there. Oh, you're going to try and jump on my... Oh, please don't do that. Here, get down. Come on, get down. All right, let's go over the answers here. So we'll just put these over here. And we'll just get rid of all this. All right, so for S2 minus, we're going to write that as if it were... Let me move this over a little bit. As if it were some ion with 2 extra electrons. So that would be argon. So that would be neon, 3s2, 3p6. And there you go. For copper here, I got a little extra dot there I got to get rid of. Let's just write the regular electron configuration to start, because it's going to be a cation. And that would be argon, something like that, which you should then say, oh, I have a D9, I need to change that into a D10. So you change this one to 1 and this one to 10. And now we can go in and say, okay, I need to make it plus, so I got to get rid of 1 valence electron, and so that's that. And there you go. We got calcium 2 plus. So we'll just do calcium first. Calcium is argon 4s2. But I want to make it 2+, so I'm going to get rid of the 2 valence electrons, so they're gone. And so now it ends up just being argon, which we have to write as this. Then we got nitrogen, which we'll just treat as normal. 1, 2, 3. There we go. But if I'm going to make it nitrogen cation, I need to get rid of a valence electron. Now, if I have multiple choices here, and I'm always going to only have S and P to choose from, then you just go in order of energy. P is always higher in energy than S, so you take from this guy first. And that would be N+. B-. Oops, I have the wrong color. I was trying to color code these here. Oh, weird. I don't know why I did that, but that's okay. Oh, I must have something selected. So we got B-. So if I did boron, that would be 1s2, 2s2, 2p1. But this minus means I add an extra electron, because that's going to look like carbon. And then Cl2-, Cl is in the next row. But giving it 2 electrons would make it look like potassium. So I could actually just do this instead. There you go. And it looks like my answers matched up with the answers that were posted, so we're in great shape. All right, any questions about how we do electron configurations for ions? All right, then let's continue on to where we were and talk about some trends on the periodic table that are very important for understanding various topics that are going to come up later in the course. So, well, not this course, but 162 and so on. So we're going to talk about things like ionic size, atomic size, how you remove charges, the energy on that, etc. And these are all little things that are just going to be properties of elements and how we generate those properties. And we're going to need to know that information for 162 when we talk about ionization energy and electron affinity and how we calculate delta H for reactions and stuff like that. So let's talk about that today. First, we need to define how big atoms are when we measure them. And so the way that we do that is what's called the covalent radius. Or we could call it the atomic radius. Both of these are terms that exist, and they mean more or less the same thing. Now, when you have a diatomic atom that is bonded to an identical atom, so for example, like O2 or H2 or Br2 or whatever, then the covalent radius is just going to be half the bond distance. If you have an atomic substance such as helium or helium or argon or even mercury in the gas phase or vapor phase, or if you have a metal where metal ions just all line up next to each other, then you're going to use atomic radius. And so the definition of atomic radius is different. If I was to draw an atomic radius, it'd be something like this. Here's my atom, and then this would be the atomic radius. You know, just like the radius of anything. But when you have two atoms next to each other here, what you'll notice is that this part of this overlaps like so. And so part of the diameter that we should be carving at here is lost, it turns out, because these spheres overlap. In fact, if this is an electron cloud, so E cloud, and this is an electron cloud over here, this overlapping region is actually where the bond is formed. So bonds formed in overlapping electron clouds. We're going to talk about that specifically in Chapter 5, but for now, on this diagram, all we need to know is that the distance between the two nuclei is going to be a little bit less than what the atomic radius would be in a covalent radius. But that's okay, because generally speaking, we don't see free bromine anyway. Now, how do atoms change in size? It turns out that if you pick any two atoms on the periodic table, they will be different sizes, and depending on which two you pick, they may be very different sizes. There are two major trends that we're going to study in this class, and those trends are the effect of going down the periodic table and the effect of going to the right of the periodic table. So if you compare two elements in a column, or two elements in a row, you should be able to predict which one's going to be bigger, based on these effects. So the first effect is how many energy levels there are. And remember that an energy level is just our way of saying the principal quantum number, n. So if you have two atoms and one has more n's filled, it's going to be bigger. So, for instance, if I compared calcium and strontium, they're in the same column, but one has more n's. The one with more n's will be bigger, so strontium must be bigger. Going left to right is a lot more difficult. We're going to spend a little bit of time talking about that one. But there's this premise here that's probably new to you. And it's called effective nuclear charge. What the heck is effective nuclear charge, and what does that mean? Well, you might remember in chapter, I want to say 2 or so, we defined the nuclear charge of something as the number of protons it had. And so that's Z. How many protons are in the nucleus? But the effective nuclear charge, we're going to put this down here, ZEffective. And this is going to describe what electrons feel from the nucleus. Kind of as if, oh, instead of 20 protons in the middle, it feels like there are 2. And we'll explain why that is on the next few slides. We're going to come back to this slide a little bit later. But what we want to observe on this is that the sizes of atoms tend to do this sort of thing. They start really high and then they drop, and then they start really high and then they drop, and they start really high and then they drop. And you'll notice that each time we start a new period, that is, we go down to the next row on the periodic table, the atoms get way bigger. In other words, the electrons that you are adding onto your atom are quite far away. Oh, excuse me, I had to yawn there. When you add more protons to the nucleus, even though you're adding more electrons, the effect is that the size tends to go down. So generally speaking, as you go down a group, so moving down the periodic table, atoms get bigger. As you move from left to right along a row, atoms get smaller. And that seems a little counterintuitive, again, because we're adding electrons. But we're also adding something else, and we'll talk about that in a second. All right. All fundamental properties of charge follow this rule. And here it is. This is called Coulombs Law. Now, before you look at this and go, math! No! I thought we weren't doing any more math. Well, we're not. We're going to get rid of this thing right here. And we're going to do Conceptual Coulombs Law, which is basically, I throw out all the constants, because they're constant, they're just numbers. Don't give a shit about numbers. And I want to interpret what these things mean. Oh, and the R. I forgot to put an arrow for R. Now, if you have seen Coulomb's law in physics, you'll notice that, oh, our term only has an R on the bottom. You might have seen this equation where there's some constant Q1, Q2 over R squared. And you'll notice that I wrote the letter F here instead. Oops. Well, I had the letter F and then I messed it up there. There we go. I wrote the letter F instead of the letter E. E is an energy, which is in joules. F is a force. And using the formula for work, I could say force times distance would give me energy. And so that's why I only have this R term here. Okay, so be really careful. If you have a physics background, this is actually something that can mess you up. And you might go in here thinking, oh, it should be R squared. Well, it's not, because it's energy. What do these terms mean? First of all, Q is the charge on our entity. So, like, if we have a proton, it would be positive 1. If it was an electron, it'd be minus 1. If it was a lead 2 ion, it would be plus 2, or whatever. And so the charge symbol is going to matter. The reason being is because if I multiply two charges together and they are the same, what is the result of the operation? What happens when you multiply two positives together or you multiply two negatives? What's the sign on the result? Well, you get positive. Positive signifies repulsion. If you put a number into the Coulomb's formula and you get a positive number, that means that those entities repel each other because their charge is the same. But if I have two entities that have a different charge, I will always get a negative number, and that represents an attraction. The magnitude of the number, or the absolute value, tells you how strong that attraction is. If the magnitude is very large, things will be stuck towards each other very strongly. If the magnitude is very low, there will be almost no attraction, and it'll just be like the two things don't interact with each other at all. Finally, the last thing that we have here, R, is distance. And as you move electrons away from the nucleus, they're less attracted because they don't see the force of the nucleus as much. Alright. Text is probably going to appear over what I have here. You don't need to know what the constant is, so epsilon 0 is what's known as permittivity of space, and it's just how effectively charge crosses a distance in a vacuum. This is all we were talking about, so we're just going to highlight the important things here, what I just said before. So, oops, that's not the highlighter. I have the wrong color. All right. So we care about the sign. And we care about the distance. That is all we care about. So let's use this to explain some stuff. If you are an electron and you are flying around the nucleus, you are feeling two things, assuming you are not hydrogen. And that is the following. Oops, I clicked on the wrong thing here. All right. So let's draw my atom here, because what we're going to see is that something happens. Let's do that. All right. I'm going to ignore neutrons just because I don't want to make my drawing more complex than it needs to be. So in my beryllium atom here, I have 4 protons. And so, oh, I just noticed the question. So the formula that we have on there is not to find the radius. R is just the distance between 2 points in physics. But D is also used for that as well. It has nothing to do with a radius necessarily. This is just to show how strongly 2 things are attracted. I'm going to write that on the screen here again in a second. So I have 4 protons in the nucleus, and then I have my 1s electrons. I'll just throw them here for now. In the 1s orbital. And they could be anywhere in here that they want to. And then out here, in the 2s orbital, well, I would have my other electrons. And I'm just putting them all on the same side for the purposes of arguing what I'm going to argue. Because they could be anywhere, but the effect will be the same. Let's look at this electron right here. I'll underline him in red. What he is going to feel is a pull towards the nucleus with a force, or ZEffective, of 4+. And the reason for that is because there's 4 protons in the nucleus and the electron's right there. It's going to feel all of those forces. Now everything else is going to try and push this away. But it ends up pushing it in such a way that it's just going to be lateral from the nucleus. It's not going to actually be interfered. But now let's look at this electron over here. This electron is also pulled towards the nucleus. Excuse me. But at the same time, other electrons are going to push it away. This guy just pushes laterally, and so we don't get much effect. But these guys are actually closer to the nucleus than our electron that is feeling the force of this. So because of the electrons that are closer, or the core electrons, it's still attracted to the nucleus, though. And that attraction will hold the electron there, but not as effectively as it could if those electrons in the middle just weren't in the way. And so this leads to the concept of effective nuclear charge. The effective nuclear charge is how much force outer electrons feel from the nucleus. And the way that we calculate it is with this formula. ZEffective equals whatever the atomic number is minus the number of shielding electrons that are core. Now, looking at our diagram here, you could easily say, oh, well, there's 2 electrons that are pushing back, and there's 4 protons. 4 minus 2 is 2. And it turns out that that's the right answer. So that's how we calculate ZEffective. So to calculate ZEffective for these outer electrons, I would first calculate the atomic number, and then I would subtract how many core electrons block the nucleus. And that would be this guy and this guy. So the force that the electrons on the outside feel is positive 2. Which means that those electrons will be pulled with a force of 2, we'll say. Now, if I were to go down here and draw the same thing for a different atom, we'll say boron or something. So here's my 5 protons. I get the same situation for my 1s electrons. And 2s and 2p are roughly the same energy, so I'm just going to do this. Now remember, if I have the same N, these are all valence. And so they are roughly the same distance from the nucleus. So these guys, even though they're a little closer, they don't really provide much push outward. But these ones do. My electron on the outside is still pulled towards the nucleus because they have opposite charges. But these are the electrons that are actually going to screen that charge out because they're core. So to find ZEffective here, I would say, what's the atomic number minus the number of core electrons? I have 5 protons in the middle. I still only have 2 core electrons. That means that for this atom, which is boron, this electron is being pulled on by a force of +3. Now, if up here, my electron that I'm looking at in my problem is being pulled on by a force of 2, and down here, my electron is being pulled on by a force of 3, which force will pull the electron more tightly? 2 or 3? And remember Coulombs Law, which we'll put over here. What do I have to put in for a Q to make it have a stronger pull? Yeah, I picked the bigger number, right? Because if I put 3 in here, this number for E will be 3 times as big as if I put 1. And it'll be certainly bigger than if I put 2. So what we have learned here is that as ZEffective increases, atoms pull their electrons tighter to the nucleus, and thus they get smaller. So ZEffective is kind of the secret to quantum mechanics and all these trends. If you can calculate ZEffective, you can do virtually anything in quantum mechanics and make any prediction you want to. And it turns out that's entirely because of Coulombs Law. Because ZEffective is just the number that you're going to plug in for the nucleus. Now, here I got +2 at the top, and down here I just got +3. And I had these guys here that I said, they're not really closer. And you might have been looking at that and saying, what? Huh? I mean, you drew them closer, right? But their valence, are they really not closer? And the answer is it's kind of sketchy. This is a first-year course, and you might remember that I was talking about last Thursday how we're going to sort of hand-wave the rules for figuring out valence electrons and distance and so on and so forth. And I mentioned something called Slater's rules. Slater's rules are the rules for calculating ZEffective to a much more effective degree. In this class, we're going to use this formula to calculate ZEffective. But if you go and do your own research and look up Slater's rules, the formula for ZEffective is actually way more complicated. It has the first part that we do, but it also has another term where it's like, for things that are n-1d, they count as 0.7, and if it's nd, they count as 0.2, and things like that. So you do a bunch of fractions, and you end up with this very granular way to calculate ZEffective, which is cool if you're not a first-year student and already overwhelmed by this shit. So we're going to stick with the simple formula, which is actually going to provide us a lot of information as it is. All right, so let's do some calculations on how to figure out ZEffective. This slide right here is just saying what I was talking about. If this is my electron on the outside that I'm looking at to try and figure out ZEffective, because it's the valence electron, I'm not selecting the pen. There we go. Here's my pull towards the nucleus, but here's my repulsion, because these electrons are closer. Any electrons that are in the core, again, not valence electrons, are going to repel valence electrons further away. And so those are called the shielding electrons. You may see this in other textbooks as called the screening electrons, because they screen out the charge. They're both the same term, and it doesn't matter which one you use. If I wanted to calculate ZEffective here, for this atom, which is lithium, first I'd write down the formula. Lithium has 3 protons, and there are 1, 2 core electrons in the middle. So its ZEffective should be +1, and it is. All right, let's do a few more of these, and then we're going to start doing some comparisons to see if we can figure out any patterns here. So what is ZEffective for chlorine? Without drawing any pictures, you might think, oh, this might be a little more difficult. But just write down the formula first of all. I think the hardest part is remembering what Z is. Z is the atomic number, so you just go straight to the periodic table and find that. Finding the core electrons is also difficult because how do you know which electrons are core in chlorine? Well, the real way to do that is we're going to have to write out the electron configuration. And we should all be adept at doing that by now. Now, once you have written down the electron configuration, you should be able to determine which electrons are core electrons and which ones are valence, because valence electrons are in the highest n. Which means that everything else is the core electrons. And if I count the number of electrons in here, which is neon, I get 10. So ZEffective for chlorine is 7. That means that the protons in the nucleus pull on the valence electrons on the outside, the 3s2 and 3p5 electrons, with a force of 7+, which is actually rather high. Those electrons are pretty much stuck. They are not going anywhere. All right. Let's do another one. Let's do boron. We already did boron, so I'm going to change boron to... What do I want to change this to? Let's do aluminum instead. So write down the electron configuration for aluminum on your paper. And once you've done that, you can look at the screen and see if you got what I got, which is this. I almost just said the answer. That doesn't help you. And then let's fill in the formula. ZEffective is Z minus core electrons Z for aluminum is 13. Core electrons is just the neon again. I got +3 for my answer. Now you might notice, well, wait a second. For boron, when we did it on the PowerPoint window, or the Photoshop window, sorry, I also got 3+. Is there a pattern here? Turns out there is. What might the pattern be? In fact, if you aren't sure, what you can do... Oops. We could just do this as an exercise for a second. If you want to figure out the ZEffective of these elements... What would ZEffective for each of these elements be? I'll give you a second to calculate it, and then you can type it in the chat. Does it correlate with the number above each row? So the group number, and the answer is kind of, depending on what periodic table you have. So if you have the one that has labels with A, 1A, 2A, 3A, 4A, etc., then yes, it does line up. If you have the one that just numbers them 1 through 18, then if you get rid of the 1 or the tens digit, it does work that way too. But for B groups, it doesn't quite follow the formula. And we'll show why in a second when we talk about transition metals. So what would ZEffective for all of these things be? Well, I'm going to write out the electron configurations of these real quick, and we'll see if we can get some information here. Let me just erase this because I need this space. And if I do ZEffective for each of these, sodium's got 11 protons, neon's 10 valence electrons. That looks like the letter H. It should be a 1+, but... There we go. That still looks like an H. I tried. And you're going to notice that you get the same thing each time. So if you go down a column, ZEffective remains the same because the number of shielding electrons changes, but the number of protons also changes. And it changes in such a way that you get the same result. If you go left to right, ZEffective increases because when you add electrons, you're adding valence electrons. And valence electrons don't screen out charge. They just are on the same sort of level. They push laterally. All right. And valence electrons correlate with the group number. That's right. Especially in the main group. So anything with an A designation, those will line up very specifically. So, for example, anything in 3A will always be S2P1. Now, explaining why atoms get bigger and smaller as we move in certain directions is a little more difficult. We're going to use our diagram to do that. Did I select all? Oops. Oh, no, 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 no. That is not what I want to do. I almost deleted my scene in OBS. That would have been really bad. I want to make sure I'm on this screen. Okay, good. Your screen would have just gone blank, and I would have had no way to fix it without taking the stream down and building it again. That didn't fully appear. That's okay. All right, so let's look at our periodic table, and I'm going to up in the corner here where you can't see. Hold on. Okay, that's what I can work with. This is going to be a little like rudimentary sketch of my periodic table. And so we're going to measure the effects as you go this way and as you go this way. So let's start with top to bottom first. Let's consider two atoms that are next to each other. So we got magnesium and calcium. If I draw an electron configuration diagram for each of these, magnesium's going to go up to about here. I'll just do this. But calcium's going to go further. So the question is, who's bigger? Magnesium or calcium? Remember that at the bottom of the diagram, this is my nucleus down here. Surprising absolutely nobody, calcium is bigger. So as you go down the periodic table, the number of energy levels that are full increases. Therefore, we would conclude that the size of the atom must also increase, because those electrons have to go somewhere. They cannot just all cram together into a singularity. That would just lead to electron-electron repulsion, and then that would require more and more force to hold them in. Is francium the largest? It is the largest. It's the biggest atom on the periodic table. But could you explain that using quantum mechanics? And that's what I'm trying to get you to do here. So now that you know the trend, you could pick francium as the biggest one. Which one's the smallest atom on the periodic table? Probably before today you would have said hydrogen, but it's not. What is the smallest atom on the periodic table? In terms of radius. It is helium. There you go. Very good. Alright, so we've explained going down. As n increases, size increases. So as you go down the periodic table, atoms get bigger. Hee hee. Now, as you go left to right, atoms get smaller. And the reason for this is the following. So I gotta... Oops, that's not what I meant to do. First, I gotta do that. I don't know what's going on here. Hold on. It's because my install Photoshop is all screwed up. So I want this stuff to go boop. I should probably just use the mouse for this. There we go. So now what we're going to consider before we take our break is ZEffective. So I'm going to pick two elements that are next to each other. We'll do nitrogen. No, I won't. I've selected the wrong thing. We're going to do nitrogen and oxygen. And if I calculate ZEffective, I would get these numbers. Which means that my electrons, when I draw the diagram here, would be attracted to the nucleus with this force. So there's my nitrogen. And these electrons right here in n equals 2 are being pulled down towards this with a force of +5. Now, be very careful. Don't draw your oxygen in just yet, because you're going to see what happens with my drawing in just a second. So, don't copy this exactly what I've drawn yet. Here's my oxygen, and these electrons are being pulled with a force of 6+. But because 6+ is larger than 5+, what that means is that these guys are pulled with more force and should thus be closer to the nucleus. And you can see what I did there. So now when I compare the elevation of these guys, I get nothing because I don't have the whole canvas selected. And since energy and radius are roughly proportional to each other, these electrons end up being closer to the nucleus because ZEffective is larger. So what that means is in our energy diagram, if we were going to draw these correctly, we should draw the energy diagram for O with all the orbitals slightly closer to the nucleus than for N. And I'm sure I've mentioned that before when we were drawing energy diagrams, that as you add electrons and they get attracted to the nucleus, everything starts to sink down. And this is why. Because when you add electrons, you're also adding protons. And the more protons you have, the better they are at pulling those electrons in, at least until you add a new N level. When that happens, then the electrons go very far away and you have to repeat the process again. All right, so to summarize now, let's go back to this chart here and see if the trends that we observed holds true. And again, so these right here were my new N's. So as I go down a period, as I go down a group, N increases, and so the size increases. So this is N equals 2, 3, 4, 5, 6. And then as I go across a group, oh goodness, I'm getting my terms all mixed up because I'm looking at this diagram. As I go across a period, so this is period 2 right here, ZEffective increases. And so this would be ZEffective is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8. And you can see that as ZEffective increases, the size of these atoms, more or less, gets smaller. There are some hiccups in there because quantum mechanics. You can't see because it went off the screen, didn't it? Yeah, there we go. Sorry about that. So for period 2 here, as ZEffective increases, my atoms get smaller. For all of the periods, as n increases, the atoms get bigger. Now, when we come back from the break, we're going to try and answer what's going on in here. Because transition metals don't follow the rules, as we've already found out. Transition metals don't behave very well at all, and there's a specific reason for that. We're going to do the ZEffective for that in a second, but if you want to try it yourself, do the ZEffective of, say, titanium and then vanadium, and see what you get for your answer. In the meantime, also, you should take a break, because we went over like by 10 minutes before our break. So let me get the timer up here. Boop. Boop. Alright, I'll see you in 10. Boo. Womp, womp, womp. We'll just hide those. Alright, so let me get back to where we were. I actually am going to skip a few slides here because it's just stuff that we've already talked about. We're not going to talk about ionization energy just yet. But we will get to the examples. And then before I have you try it, I'm going to show you some transition metal examples. So let's compare lithium and beryllium. Knowing that lithium has a ZEffective of 1 and that beryllium has a ZEffective of 2, which atom is smaller? So type your answer in the chat. Which of these is the smaller atom, lithium or beryllium? And it is beryllium. Very good. So again, the atom with the smaller radius has a larger ZEffective. And that didn't erase everything. There we go. We already did this one. Which is bigger, O or N? And we said it was N because O has a larger ZEffective. Now, you do have to be very careful with how I ask these questions, because I might ask you for which is bigger or which is smaller. And depending on what I ask, you're going to get a different answer. So be mindful of that. All right. Before we talk about ionic radii, we'll do that in a second. Let's go over here. That's the wrong window. I don't want that for now. What we're going to do now is we're going to try and figure out ZEffective for a transition metal. And so the examples that I gave were titanium and vanadium. So let's do titanium here. And titanium has an electron configuration of argon 4s2, 3d2. And vanadium is argon 4s2, 3d3. And we're going to figure out ZEffective. So ZEffective, again, is atomic number minus core electrons. So for titanium over here on the left, I have 2 valence electrons, and then all the circled electrons are core electrons. We're including these as core electrons because they are not in the highest N. So the ZEffective for titanium would be its atomic number, which is 22, minus all of the electrons. So argon has 18, and then these d electrons would be 20. And this is what I get. For vanadium, same situation. So these are core electrons, and these are my valence electrons. Vanadium has 23 protons, but I'm going to subtract these 18 and these 3. And what do you notice you get? You get the same ZEffective. What would we conclude about their size? The conclusion we would draw is, well, if they have the same ZEffective, they must have roughly the same size. And to our first order approximation, that's actually good enough. Because if I go back here, you'll notice that for the transition metals, specifically here here's titanium and here's vanadium. These are the two that we just looked at. The change in size is so much smaller compared to elements before it, or around it even. So these guys are almost exactly the same size. And the reason for that is they have the same ZEffective, therefore they have similar sizes. I don't know what that letter was supposed to be. Now, why can we only get that level of determination from our calculation? And that is because we're not using Slater's rules. So if we gave D electrons some amount of shielding, then that would affect our result. We get a more granular result, and we'd be able to differentiate that fine level of detail there. But when we're just doing crude measurements with ZEffective minus, or Z minus shielding, we're going to get 2 every time for transition metals. Unless it's in groups 4 or 9, then we're going to get 1. But for our purposes, this is good enough. ZEffective is approximately 2 for any transition metal, and so you get approximately the same result. And you can show that with pretty much any transition metal that you want to. All right. Going back over here, this next section talks about ionic radii and how their size changes. If you have lots and lots of electrons, atoms are big. If you remove the electrons, atoms are small. Now, in this diagram over here, and I'm going to use these two to describe this, as you take away electrons, the electrons that remain are pulled closer and closer to the nucleus. If I draw an energy diagram here, in this space, for lithium, which is 3+ in the nucleus, and beryllium, which is 4+ in the nucleus, if I were to ionize these by removing these electrons, as shown, so this goes away and this goes away, then the force pulling these down is just the full force of the nucleus. There isn't any ZEffective for these electrons in the 1s orbital. They're just right next to the nucleus. They feel the whole thing. Because 4+ is stronger than 3+, this ion is going to be smaller than this ion. So for ions, it works the same way, but you're going to have to reconsider what is now the valence electrons and now what are shielding electrons. In beryllium's case, there are 4 protons, and none of the electrons that remain are shielding. Down here for sodium, if I remove 1 electron to get sodium+, 10 of the electrons that are there... Oops, sorry, I don't know why I did electrons. There are 11 protons in the nucleus, but of the electrons that are present, there's 10 total, but only 2 of them are shielding electrons because they're the 1s2 electrons. And you actually end up getting 9+ for ZEffective for sodium. And the reason that you get 9+ is just because of how the formula works. Z minus core electrons in sodium plus. If I write sodium plus as electron configuration, I don't know where I'm going to put this because there's not enough space. We'll do it here. So Na plus is just this. There's that helium I said I would never draw. And then this right here are my 2 core electrons. Everything else is a valence electron. So that changes the formula. I get 11 minus 2, which is 9 plus. So for ions, you can actually get ZEffectives that are larger than 8. 8 being the highest that you could theoretically get for something like argon or krypton or neon or whatever. Now that explains the trends, like how do we compare the ions towards each other? But if you compare ions toward the neutral version, so for example, lithium to lithium plus, lithium is going to be much larger because it has that 2s electron. You get rid of that, you basically strip off an entire layer here. So atoms get much smaller when you remove all of the valence electrons. Oops. We're going to learn about hybridization? Yes, Chapter 5. That'll be the last thing we cover in this class. Not today, but week 10, Tuesday, probably. Conversely, if you add electrons, the opposite happens. Electrons don't like each other, so when you add electrons to fill all of the valence orbitals that are available, the atom just kind of bloats up like a balloon. For instance, if I add an electron to fluorine to make it fluoride, it virtually doubles in size. That extra electron requires a ton of space to be available in order for it to go in there. For oxygen, it requires two extra electrons to be put in there, and you have to put those in a large space. Oh, excuse me. So adding electrons to ions makes them bigger. And the entire reason for that is electron-electron repulsion. We need more space to put in electrons. I know if I yawn, I make all you guys yawn. I just felt the collective universe yawn. On this slide here is something called the isoelectronic series. And what the isoelectronic series talks about is all species that have the same number of electrons. That's what iso means. Iso means same, and electronic just means electrons. And what we're going to look at in this series are these right here. Why is it getting smaller? And the answer is entirely based on ZEffective. So let's calculate ZEffective for all of these. In order to do that, you've got to write out the electron configuration. So for this atom, we would have, let's see, I got to find sulfur. There it is. So this is, and I did 3p6 because it is sulfur 2 minus. And this is going to have the same electron configuration. And what you'll notice is that, well, they all have the same number of electrons, so they're all going to have the same electron configuration. In each case, these are going to be my core electrons, the 10 in neon. So I can do this. I have 16 protons minus 10 shielding electrons. My sulfur atom, or ion, has a ZEffective of 6+. What about for chlorine? You could do the similar treatment and get these answers here. Actually, I guess I'll just show you the math. So this is the same thing. And again, the number of core electrons is not changing in these examples because they all have the same electron configuration. The core electrons are just whatever the neon core is. And so, again, as ZEffective increases, what do you notice? hopefully you notice that the atoms or the ions we're looking at get smaller. So the only reason that we really want to look at the isoelectronic series is because it's a good way to compare size and ZEffective. It's a direct trend. All right. We're going to use ZEffective as another gauge of strength in the next section. So the numbers highlighted in pink, those are the radii of those entities. So sulfide ion is 184 picometers, chloride ion is 181, potassium ion is 133, and then calcium is 99. So we're just showing that, oh, as ZEffective gets bigger, the things are getting tinier, and that's represented by the numbers in pink. All right. So what I want you to do, for practice, I'll give you 5 minutes to do this. Using quantum mechanics and ZEffective, those are essentially the same thing. Pick the smaller atom in each pair on the top, and then pick the smaller atom or ion on each pair in the bottom. Okay? If you're stuck, ask questions in the chat. We'll guide you through it. How are we doing? Let me know in the chat. We'll go over the answers. Unless people need more time. More time. Okay, keep going. I have all the time. I could do this forever. Oh, we have like 20 minutes left. But... Alright, so for this slide, this is basically the summary of, like, hey, do you remember the 2 quantum mechanical rules that we care about? And so those rules are, of course, ZEffective. And also whatever the highest number n is. I'm going to call that n max, just for our purposes for this slide. What we're going to do... Actually, let's do this on the sample problem slide here. I got to reveal that again. Let's see here. Where can I write? I can write here. Alright, so we're going to compare magnesium... Well, we're going to compare magnesium and calcium. Ow, come on. And so the way that I like to do this is I like to compare ZEffective and also whatever the maximum number of n is. And so hopefully you were able to calculate the ZEffective for each of these is positive 2. And then when we look at what the highest level n is, what the valence shell is, magnesium that's 3, but for calcium that's 4. So this is the difference for these atoms, is this one right here. And if you have a larger n, you have a larger atom. Therefore, which of these is the smaller of the 2? That's magnesium. Now I can do the same thing. We'll compare ZEffective and whatever the highest level n is. Chlorine and argon are both n equals 3. But if I calculate their ZEffective, I get this for my numbers. So there is the difference. And for the larger ZEffective, I have a smaller atom. And since that's the question I want, that must be the answer. Uh-oh. They're doing more yard work outside. I apologize if you hear that. Well, I don't even know what that is. I think they're digging holes or something. Wrong color. There we go. For sulfur and oxygen, we can do the same thing. So sulfur is in period 3. Oxygen's in period 2. And they both have 6 for their ZEffective. There's the difference. Larger N means the larger atom, so this must be the smaller atom. Alright, what were the last questions here? Alright, and then finally, using quantum mechanics and ZEffective, explain which atom or ion in each pair is smaller. For the first two, we don't really need to do much work here. This one's obviously smaller because cations, when electrons are removed, the next layer down becomes the valence layer, and its ZEffective is much, 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 much bigger. For this one, same thing. Adding electrons increases electron-electron repulsion. They take up more space. So this one must be smaller. But for these two, we gotta do something like this. So they both do n equals 3 as their max. So that's not going to help us. But looking at ZEffective, chlorine is still 7, argon is 8. Bigger ZEffective, smaller atom or ion. Alright, that is our conclusion for ZEffective. Are there any questions about what ZEffective is, or how we determine which entity, or particle really, in a comparison, I'm trying not to yawn here, in a comparison is the larger or the smaller of the two? Leia's going to yell at me if I yawn again. We don't want that. Alright, so the next thing that we're going to talk about is ionization energy, and we're only going to do this for like 4 or 5 more minutes, because we're almost out of time here. But I do want to define what ionization energy is very quickly, so that you'll know this when we come back on Thursday. If I have electrons in my energy diagram, the highest level that they can get to is infinity. If I remove my electron by moving it up to n equals infinity, this electron is so far from the nucleus that there is no energy of attraction here. And so this process is called ionization. Because what we have done is we've removed the electron, and we have created an ion. This is now, whatever this atom would be, it would have a positive charge. If you do this one time, then the amount of energy that it took to do that is the first ionization energy. If you did this multiple times, then that would be the next ionization energy. So the second ionization energy would be the energy to remove the second electron, and so on. As you remove electrons, ZEffective may change because the number of valence electrons might have become 0, and then the next layer down becomes the core. Also, any electrons that remain in the valence shell are pulled tighter towards the nucleus. So, for example, if I had this electron as well, before, the nucleus would be pulling on these both equally. But if this guy is just gone, now all that's left is this electron to be pulled on. And so that force gets focused on just one electron. And so everything gets pulled in just a little tighter. So as you remove electrons, it gets harder to remove the next one, because this one will be held on slightly tighter than the previous one. But if I get rid of this one too, and then now I start looking down here, these are going to be way harder, because ZEffective is higher. So looking at ionization energies can tell you something about the atom. The next thing that we want to care about is that whenever we talk about ionization energy, it's always a positive number. You always have to put energy in to remove an electron. Otherwise, electrons would just come flying off of atoms on their own. And they don't. Which is fortunate. We don't want our electrons to go just hurtling into space everywhere. I think I have a picture of the ionization energy. We're going to explain this picture on Thursday. But for now, what do I care about that I can do in like 5 seconds here? Not really much. You're going to notice that ionization energy is related to the same concepts we just talked about. So, what is the highest N, and what's the effective nuclear charge? And it's basically the same as radius. If an atom is small, it's going to be hard to ionize. If an atom is big, it's going to be easy to ionize. So, with that in mind, do read over a little bit of this section. We're going to come back on Thursday, and I don't know how much longer this is going to be, actually. Where are we on the slides? We are here. So we're going to do ionization energy and electron affinity on Thursday. Probably talk about the periodic table. This will probably stretch into Tuesday next week, but we're definitely almost done. Thursday will be the end of quantum mechanics. Like 100% certain. There is extra stuff that kind of segues into Chapter 4, which is just like molecular and covalent compounds and how to create them. But we're going to do that mostly in Chapter 4. So we are almost done with quantum mechanics, which means that we won't have to see the dark hour here for too much longer. But in the meantime, I'll still play the gloomy, oppressive music, just because it's thematically appropriate. I want to thank everyone for coming out today. I'm going to unlock lab number 4 right after I take the video stream down. Please look over it, because lab number 4 is a doozy. That is why it took me so long to make it. You are basically going to be calculating 50 to 100 orbital transitions in lab number 4 in Google Sheets, and I'm going to show you all about how to do that tomorrow. So really, really important. If you are not proficient with Google Sheets, make sure you come to the lab lecture tomorrow, because I'm going to show you how to do it on screen. And you practicing along with me might be helpful for you. So look forward to that. When Chapter 3 is completely done, there will be a quiz number 3 up. It will be very close to the end of the quarter, I realize, because you've only taken 3 quizzes, and then suddenly here's 3 more. Kind of unfortunately just how that's going to work. But yeah, nothing due yet today. Nothing due tomorrow. Nothing due Thursday. Should be a nice, breezy week for Chem 161 work. Thanks for watching. Make sure that you stay healthy, stay safe, stay at home. See you tomorrow.